do some more Erlang today. I'm just getting started. It's one of those days where it's been really hard for me to get moving out of bed, out of the couch, out of everything. I feel like just so tired today. So I wanna I wanna you guys, if you're learning Erlang with me or whatever, I think it's great if I seem kind of excited about what I'm doing, but some days it's just hard. All right, so let's get into the mental. Let's lock into Erlang and the mental model that we're going to be working with. Um, I ordered like a camera stand that can like point down. So what I'm really hoping to do is like start doing some more embedded programming and like breadboard work, maybe even soldering. Learn how to do that, and that will be kind of fun. So we'll see how that goes. It'll be neat. And I can kind of probably do like a Elixir Nerves tutorial on how to program like the Raspberry Pi Zero, things like that. That'll be fun. Um, okay. So I made an Erlang playlist, so you can kind of look that up. It has the first video if you missed it. And we went over some basic stuff. We're using this book, Learn You Some Erlang. In the first video, I added some of these details. We did the introduction a little bit, talked about the shell, although I don't really remember it much. Then we got into the data types. So we have numbers. The funny thing is like all these statements have to end in period. So that's kind of weird. We learned how to do variables. Variables have to start with a capital letter. And the equal sign is pattern matching. So this isn't checking for equality. It's just saying like match the stuff on the right to the left. And since they're the same number, they match. So, well, in this case it doesn't, but here it does. And here it doesn't. So you're not getting an inequality error. You're getting a match error. The underscore means we don't care about it. We learned about atoms. It's lowercase, can have underscore after the first one and an @ sign. And also you can quote it if it has other characters in it. And this becomes an atom also. We learned about some Boolean operators for equality. This one was a weird one. What's the use case for it? So I came in through it with, I'm interested because I went to an Elixir conference and I use Elixir. I love Elixir, and it's based on the Beam virtual machine. And where did Beam actually come from? It was created when Ericsson, a Swedish telephony company, needed a programming language to keep their telephone system up and running. So it's really, really good at very concurrent parallel stuff. And hi, Eric. Good to see you again. It's been a while. I've been disappeared for a bit. But anyway, so because it uses something called the actor model, you don't need to deal with like threads and locks or promises and all that kind of stuff. Every single thread is they call it a process, and they communicate with other processes through message passing. So when you do message passing, that's the only way that they communicate with each other. You never have to worry about locks. You're basically like single threaded when you're alone. So that's why it's really good. I use it in Elixir, but Elixir is built on the same virtual machine, Beam, but it's more modern looking. Erlang was the first language that's built on it. You might have heard of Gleam also. Um, and that's another language built on top of the Beam VM. Companies that use it, Discord uses it because of the high number of users that are concurrent in the system. Um, yeah, WhatsApp uses it. So you may not have heard much about these, the use cases. It's not the sexiest language, maybe, but it's so beautiful to use. They are functional programming languages. But Erlang is like from 1986. So it has like, you can see some of its like old style syntax quite a bit. Oh, you released your game. Congratulations. I'll have to check out your channel to see the latest. Oh, that's so awesome. I watched several of your streams or like recaps afterwards. That is so awesome to hear. What a big accomplishment. I'm like, I tinker constantly. I feel like nothing ever gets off the ground for real, for real. But I have a job and some things actually finished, so I try not to feel too bad about it. We learned about tuples, which is like these data structures. Let me get into the REPL here. I made a shell.nix, which basically just brings up Erlang 28. You can install Erlang yourself. Um, and then when you have Erlang installed, you can run Erl, and now I can make a tuple. So a tuple is an ordered, um, I hate to say list, but it's an ordered set of things, and and it's a definite size, so they never change. So if I do something like 5 comma hello, this is a tuple, and I can then assign it to something like a variable, like foo is equal to 5 comma hello. Ah, and now foo is that. And I can also deconstruct it. So if there's a number, I can like pull out the number and I can call this part like some string is equal to foo. I gotta turn that sound off. Oh, it's called foo like this. And now you can see that num gets the number 5 because it was deconstructed. So that's pretty cool. That's just pattern matching. When I type the wrong thing, it makes that sound, which is super annoying. I really have to get back to 8-bit assembly programming. I was trying to like hook up this Atari, the 400, which is like a retro replica of the Atari 400, to my um, Elgato Capture card. I don't know if you can see any of that, but it doesn't work. So I have to figure that out. Otherwise, I can go back to the emulator. I also just bought a Commodore 64 from the newly re-released Commodore.net. So that'll be really cool. I wanna program with it. It has an HDMI out also. So maybe there'll be some way for me to stream that. I know like you can stream all of that from the emulator. It just doesn't feel quite the same, right? Like it'll just feel, maybe it's just me, like for you guys it's all the same, but it just feels cool typing on the old computer? Hi Findus, how are you today? What's going on? Trying to continue with where we left things off. All right, so then we learned about lists. I won't go into all of that, but it looks like this. By the way, this book is called Learn You Some Erlang for Great Good. It's available online at this link. You can find that in the video last time. In the last video, it has a link in it. I'll add it to this one later. All right, and then there's some operations for concatenating lists, removing items from lists. basically constructing lists, and our cute drawing. And then we did list comprehensions, which is cool. This is probably where I start getting a little bit more confused. So let's try to remember. Here is where we're trying to double the each element in a list. So here is a list where we're going to double, right? So watch, I got a list. This is just like how I think. So we're going to start with this. And now we want to make a list comprehension. So a list comprehension, if we just want to do a regular one, like we don't modify it at all, it looks like this. Right? X is being assigned each one of these elements. Assigned, what's a better way to say it? It iterates through these, and then the value itself is X. But now I'm going to change this to be 2x, 2 times x. And now each of the elements is 2, 4, 6, 8. But I want to say something like, I only want the even numbers, which will be 2 and 4 here, right? So we put a comma afterwards, and we take the number x, we use remainder, 2 is equal to, and their equal to looks like this, 0. And now this will filter out 1 and 3, we'll only have 2 and 4, then we double it, and we have 4 and 8. How cool is that, right? The other thing we can do is give it 2. These things are called generators here. This part is called a generator. So we're going to make a y and a y generator, and this one will be 10, 11, 12, 13. I kind of did a bad thing here, right? Because it really should be 11, 12, 13, and 14. Let's do it like this. I don't think this will cause any errors. It's just that we won't use the y. Let's see what it says. Oh, interesting. I see. It's basically doing 1. Here, let me get rid of this remark here. I mean this remainder thing here, and we'll be able to see this better. So actually, let's get rid of the 2 also. So it's doing 1. Oh, I see. What it's doing is it's doing 1 for each one of these. You see, 1 comma 11, but we only take 1. 1 comma 12, but we only take 1. 1 comma 13. So basically, for every element in the y, it's going to repeat itself, right? So if I add a 15, 16 instead of 4, we're going to have 6. 1, 2, 3, 4, 5, 6. That makes perfect sense. Yeah, Eric, using real hardware is just so cool, and I feel like I'm in this hardware arc of my life. Where's my hardware box? My talk went really well. I hope there's going to be a video soon. I got these ultra sonic sensors that I used in my project. I got the Raspberry Pi. I got some e-ink displays and OLED displays. I want to use those too. I think I got a microphone detector, and what is this? No, that's the e-ink. I think I have some other sensors. I just can't remember what they are. I have a light intensity sensor somewhere in here. Where did that go? Here it is. BH1750 digital light intensity sensor module. I haven't used this one yet, so I want to play with this. It looks like it has 4 pins. One is going to be power and ground. I'm trying to read this. It says GV SDA and SCL or something. Anyway, we'll have to figure out what those pins are. Anyway, we're getting sidetracked. All right, so what was I doing originally here? I added a y, right? All right, so this is going to repeat itself because it finds the even numbers here, and for the even number 2, it's doing 2 comma 11, and it says 4 because it's only taking the x. But if I bring the y in here and I make it a tuple, you can now see, here I can just do x comma y. Now you see the tuples for each one. It does, let me also get rid of this. Right, so now you can see it here. So 1, comma 11, 1, comma 12, 1, comma 13, 1, comma 14, and then we switch 2, comma 11, and so forth. So that's what it's doing here. And then if I say I only want the even x's, I just put it in here. I just do x remark remainder. Why do I do that? Is equal to 0. And now you can see I only have the 2 and the 11, 2 and the 12. So it's still going to do all the y's. And I guess I can also probably say y remainder 2 is equal to 0. And now we're going to have the same number of them, but they're all going to be even numbers. Does that make sense, everyone? Okay. I just find like some of these things when I know, like, you ever get the feeling that like something's a little bit not clear in your head? In English we say we're confused, but it's like, what are we confused about? I couldn't tell you what's foggy in my head, but it's just like I know I don't have a lot of practice with it. So this syntax, I just feel like it's good to do several times, and that's useful. So we can do 2 times x, 2 times y here, and now instead of 12, we get 424, right? So that all makes sense. Yay, you're following. Awesome. Also, I switched sides on the browser and the thing, so I think this is easier for you guys to read. If you think if anything should be like larger font or something, let me know. I can't imagine anyone actually watching this on a phone. Can you actually read anything if it's on the phone? Let me know. Like it just seems like it'd be too small. Get on a computer, put it on your full screen or whatever, or just listen to me chat so that you can go to bed. All right. Yep. The pattern matching here is really cool. Let me try to figure out something here. So let's have on phone, and no, I can't read it. Oh no. You know what, Eric? Tell me if anybody else has had this problem. Like, I love learning about new technology, especially new programming language. That's why I'm always like blabbing about, programming languages, right? But like, it's almost always something they're like reading, like on, you have to see it on the screen or whatever. What I would really love is like those language things where you like listen and repeat and do things. Like, it's just I want to learn things while I'm commuting or outside or whatever, waiting for the train. And it's impossible to find any programming stuff where you can actually follow just by listening. So I try to make an effort to describe what's going on in case anyone actually just wants to listen. But I probably do a poor job several times. So just let me know. Um, I'll try to describe some of the brackets. So yeah, lists are brackets, you know, square brackets with comma delimited elements, and tuples are curly brace with comma delimited elements. So that's what we're dealing with so far. Thanks, Eric. I like your style also. There's probably some similarities in our style. We're just like talking while we're doing our stuff, right? Um, so it's not too surprising. So this is really neat, like how they're doing. I say I'm going to try to like describe things, and I say it's really neat how they're doing it without like saying what it is. So we're going to try to use pattern matching to actually constrain the elements that we get back in the list comprehension. So let's make a list first, something kind of funny. We'll make a tier list of programming languages, okay? So programming languages will be an atom. So we'll have TypeScript and yeah, should we make it a string? Maybe we make it a string. Okay, and it's going to be a list, so it's bracket. And then each element in the list is going to be a tuple. The first element's going to be the language, so it's a string, and the second element is going to be an atom that represents where it is on the tier list. TypeScript, I would say, I mean, it makes JavaScript better, so maybe I'll call it like B, right? B tier. That's an atom because it starts with a lowercase. And then let's pick another one. Rust. Is it S tier or A tier? I guess we can call it S tier. I like Rust. Of course, I love Elixir. So we're going to make Elixir and we're going to put it in S tier. What else is there? Anyone else have a favorite programming language or something they like? Java is another one that a lot of people know. I do not like Java. I'm going to put it in B tier. And then C++, I don't ever want to touch it. So we're going to put that in C tier. Right? So here's our list. Here's our tier list. All right, so when I close everything off, you see that it prints back the tier list, right? So we'll just like assign this. Oh, C. You know, C isn't bad actually. Like I like C. So let's put C in here. C. I would put this in A tier. It's just like simple and easy and historical and so important. So I'm gonna call this A tier. Oh, I started changing the naming convention here. Everything should have tier in it. C tier, A tier. So there's a language called Zig that is a lot like C apparently, but more modern. So I'm really curious to try that out someday. All right, so we have our languages here with their tier list. And obviously we can turn this into a list comprehension. First, let's call this tier list. So tier list equals, and I'll pass in this list. And now I can just type in tier list anytime and see it, right? And now we're going to do a list comprehension. First, we'll just print out all the tuples. So we'll say T for the tuple, the two vertical bars for the set. And then we're going to have T be the tier list. And now this will just this is doing nothing. It's just printing back the same thing, right? Eric says, I mostly think in C and translate into other languages. Yeah, that is kind of old school. I haven't touched C in so long. I remember I was doing C and I did C++, and then for a while I did C++. I was into it because, you know, object-oriented programming was so cool and everything. And then I tried to go back to C and I was like, oh my God, this was really hard. I can't remember exactly what was really hard. Probably just the typing, the references to things. I don't remember. But I remember that being a hard thing to do. But yeah, now I don't even want to touch C++ because I just remember so many times where finding things or multiple inheritance or whatever would just be like such a mess. I think HyperTalk is living rent free in my head now. Yeah. I know you've been using a lot of HyperTalk. It's one of those things I'm curious about to check it out someday. All right, so you can see here that we're just basically deconstructing the tier list here, right? So instead, if I do something like language, comma, tier, right? So I'm deconstructing the tier list into this. I can just now print out lang, and you see that it's just printing out TypeScript, Rust, Elixir, Java, C++, and C. So this is how pattern matching sort of works. I've deconstructed the tier list by making a tuple that has two elements in it, lang and tier. Those are variables. And then when I output, I can just do lang, and I get that. But now I want to say I only want um, items where it is S tier, right? So I can put a comma here, and then I can say tier is equal to, and what did we call our tier? S tier. And now you can see it only gives me the languages back, Rust and Elixir, because those are in my S tier. Now you can probably, if you're thinking ahead, you don't have to put this as a conditional here. You can just abuse pattern matching. And when it says tier here, just put down S tier. This is the Atom S tier. And now it's just going to return Rust and Elixir because the others won't match. And when it doesn't match, it won't go into here. It'll skip it. So there you go. Pretty neat, right? That was my review of list comprehensions. Now we're going to start learning new stuff. That was all what we looked at last time. We're going to do bit syntax now. I hate bits, or what, bit strings, or whatever you call car strings, car lists in Elixir. I'm sure this is going to be the same thing. So we'll just have to bear through this. This is like the worst part. Most languages have support for manipulating data such as numbers, atoms, tuples, lists, records, and or structs, etc. Most of them also only have very raw facilities to manipulate binary data. Oh, you like C also, Findis? Erlang goes out of its way to provide useful abstractions when dealing with binary values, with pattern matching taken to the next level. All right, next level stuff. It makes dealing with raw binary data fun and easy. No, really. No, it doesn't. This is a lie, but we'll get through it. Which was necessary for the telecom applications it was created to help with. Bit manipulation has unique syntax and idioms that may look kind of weird at first, but if you know how bits and bytes generally work, this should make sense to you. You may want to skip the rest of this chapter otherwise. What do you mean otherwise? Like, you mean if you don't know how bits and bytes work, just skip the chapter? Man, when I was doing the Atari assembly program, there was like, it felt like 20 chapters about binary numbers. It drove me crazy. Anyway, let's continue. Bit syntax encloses binary data between two angle brackets. It's like left and sign, and then it ends with the greater than sign. It's kind of like an HTML tag or XML tag, except it has two of the angle brackets. Splits it in readable segments, and each segment is separated by a comma. A segment is a sequence of bits of a binary, not necessarily on a byte boundary, although this is the default behavior. Say we want to store an orange pixel of true color, 24 bits. If you've ever checked colors in Photoshop or in a CSS style sheet for the web, you know hexadecimal notation has the format hash RRGGBB. A tint of orange is hash F09A29. So I guess that's F0 is red, 9A is green, and 29 hex is blue. So this is how we would say it. In Erlang, color is equal to 16 hash F0 9A29. Let's do that. Color is equal to 16. So this is the base that we're working with. Hash F09 F0 9829. And then that gives us the number back in decimal, right? Let me make sure that this actually works. Why doesn't that work? Oh, because it's color. Yeah, okay. 10, 16. Perfect. So this is just hex. Pixel equals color 24. I see. So color is this number, right? This big number. And then a pixel is basically saying I want to break this color up into 24 bits. This basically says put the binary values of F0 9A29 on 24 bits of space. Red on 8 bits, green on 8 bits, and blue also on 8 bits in the variable pixel. Does this make sense? The value can later be taken to be written to a file. This doesn't look like much, but once written to a file, what you'd get by opening it in a text editor would be a bunch of unreadable characters. When you read it back from the file, Erlang would interpret the binary into the nice, here's the bits, what's it called, a bit string? Bit syntax? Don't know what to call this thing. 240, 151, 41. So these are 16-bit numbers, and 1, 1, 2, 4, 8. Right, so 4 bits can basically encode the 16, no, yeah, 4 bits, that's a nibble, right? We have the 0, 0, 1, I guess we call that 1, 2, 4, 8. And if they're all on, basically that's 0 through 15. And so you would need, why are they putting in 8 bits then? Because hexadecimal goes up to, because the numbers are 2 hexadecimal values. So each one is going to need 2 of these 4 bits. And therefore you need 8 bits to store the 2 hexadecimal numbers. Like, red is 0, 9. The 0 is going to take a nibble, which is 4 bits, and the the F is going to take 4 bits, and the 0 is going to take 4 bits. So you need a byte or 8 bits for this. Octet, So that's why you do 8 times 3, and that's why you need 24 bits of space. So that makes sense why you're putting a pixel into, right, pairs of 4-bit numbers. I hate this stuff. Color 24. But how does it know to break this up into 3 bytes? Like when you have 24, why does it know to print out 3? Right? Like it could just assume, oh, I see. It probably knows because it's looking at color, which says it's hexadecimal, 16 bits. So if it's right, so let's try out this theory then. So if I change this to be I guess like 8 bits, right? And then I take just as many, I need double the number, right? So we do something like, we'll make it easy. We'll do 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So instead of 1, 2, 3, 4, 5, 6, we need 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Ah, yikes. So there's our other color. And now if I put this in other pixel, other color, 24, it still breaks it up into 3. Isn't that interesting? So even though I told it it was like 8-bit characters or, 8 bits, when I give it 24, it's just like, yeah, I'm going to break that up into that. What if I say 48? Whoops. Interesting. All right, we're going to have to read more. Okay, this basically says put the binary values of F09829 on 24 bits of space in the variable pixel. The value can later be taken to be written to a file. Yeah, we read all this. What's more interesting is the ability to pattern match with the binaries to unpack content. So here we can say pixels is equal to this thing. So this is a list of pixels. Let's copy this. So now we have a list of pixels. I wonder, I'm so confused now because how does it know how big each of these elements can be? Like, can I have something that's 2000 in here? Ah, look at that. It changes this to 82. 255. 256 goes back to 0. So, what is that, 8 bits then? Yeah, with 8 bits you have up to 256. So this must be breaking it up into everything is 8 bits, right? 1, 2, 4, 8, 16, 32, 64. No, it's more. 16 bits. So it's always breaking it up into 16 bits. All right, I guess that makes sense, right? So if I have even just one number here, if I do 256, it's just going to return 0. Yeah. All right, that's interesting. So 257 should be the same as number 1. Yep. All right, I wish they had told me that somewhere in here that these are 8 bits. I don't think it said, 16 bits. Whatever, let's continue reading. So now we can pattern match and say these are pixels 1, 2, 3, 4. Right. We can't match that many because the number isn't correct. We have 4 on this pattern match on the left, but pixels has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So instead, oh, interesting. You can give each element here a colon 24 to say how many bits it is. So if this is 6, 12, 16, oh, this math gets a little complicated. So if I do this, and I do foo 16, I'll just go like foo 1, 16, comma foo 2, 16, comma foo 3, 16, comma foo 4, 16. This should match because I assume each one of these is 16 bits. Oops, I was wrong. One, two, three, 4, 0, 0. No match of right-hand side value, 0, 0, 6. Oh, God. How does this work? Uh, oh, look at that. So this is two 16 bits. So does that mean they're each 8 bits? Am I just like doing my math all wrong? One, two, three, 4. I think I need to change the name here. Look at that. So they're all 8 bits. So each one is 8 bits. 1, 2, 4, 8, 16, 32, 64, 128. Yeah, 8-bit goes to 256. Why am I having such a hard time? I'm just being like silly. So up to 255 is 8 bits. Therefore, each of these elements is by default, if you say nothing, it's 8 bits long. Got it. All right, makes perfect sense now. Now I'm following. Which means that when we had this pixel thing here, these must all be 8 bits. That makes sense. And we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have 8 times 12, 96 bits, right? But if we do this by, instead of 8, we do 24, then we need 4 of these values, and that's why we can do this. We can say pixel 1, 2, 3, 4 and tell them they're each 24 bits. And now we match and we can do pix1, and it is this number, which is 24 bits. Okay. I understand now what a pain in the ass this was. It just does not feel easy, I guess. All right. So, right. So any of these pixels now we can break up into red, green, blue. We just break it up like this and we do pix1. Why not? That's kind of weird. I thought by default they were going to be 8 bits. Oh. Oh, I have to map. Oh, right. Because pix1 now is just a value. I have to make it a bit string. So this is like this. There we go. We have to wrap pix1 in the bit string notation. And I think like we don't even need this 8 because we learned the default was 8, right? Yeah, there we go. So you can just do RGB and then pass in pix1. We know pix1 is 24 bits, so why do we have to say this? Maybe it doesn't know. Yeah, it doesn't know because to it, pix1 is just a number. And then we have to say put that in a 24-bit value. That makes sense. All right, that makes perfect sense now. All right. We're getting there. I told you this stuff is, maybe it's just I don't like binary. All right, so let's continue reading. Oh, I didn't read this part. I just skipped it. What we did on command 3 is declare what we'll, okay, I'm just too bored to read this. Let's move on. Yeah, that's dandy. What if I only wanted the first color from the start, though? Will I have to unpack all these values all the time? Ha! Doubt not. Erlang introduces more syntactic sugar and pattern matching to help you around. Interesting. I'm thinking about a hypercard extension to chunking expressions. Tell me more. Okay, so here we have pixels, which, if you recall, was this long set of bit strings or byte strings. And we're going to match it to, we're going to pass in R8 has the first element and then do rest slash binary, which I guess is saying like eat up the rest of it. So let's try that out. So we have pixels. If we recall, it is this longer 12 item bit string. And then we're going to pattern match less than R colon 8. I don't think I need the 8 because that's the default, comma, rest in capital slash binary. And the rest is probably any word we want. Like I could call this rest of the stuff. It's just a variable. I'm guessing the slash binary is a special thing. So here we go. So now I can print out R, and that'll be the first element, which is 213. And then I can do rest of the stuff, and it'll be the rest of the stuff. So that's perfect. Chunking is a string manipulation expression, could be extended to handle numeric base conversions. Oh, okay, got it. That's because Erlang accepts more than one way to describe a binary segment. Those are all valid. Value, value colon size, value slash type specifier list, value colon size slash type specifier list. So the value is just like, you know, whatever we had before, but we can do colon 24, whatever for the bits. And let's see here. Type. Type can be integer, float, binary, bytes, bit string, bits, UTF-8, UTF-16, UTF-32. This represents the kind of binary data used. Note that bytes is shorthand for binary and bits is shorthand for bit string. When no type is selected, Erlang assumes an integer type. Okay. Signedness. Possible values: signed, unsigned. Where do we see signedness? Oh. Weird. I guess this can be part of the type spec. Oh, I see. This is the type specifier list. It can have any of these things. So it can be integer all the way to UTF-8. It can be signed or unsigned. We have endianness, which is big, little, or native. I hope I never have to deal with that. I think most things like network is big endian and everything else is little. Correct me if I'm wrong. Unit, written unit colon integer. This is the size of each segment, right? That's what we were using before. This type specifier list is built by separating attributes by a hyphen. although I'm not sure what problem I would solve with it. Just gotta make stuff and then play with it. It might spawn some ideas. Um, so let's see here. Did we have an X1? No, we don't have an X1. Oh, I see. They're assigning the X1. X1 is unsigned, and we're going to pass in a negative number, negative 44. That's funny how my editor changes that. And so X1 is actually 212. Um, that makes kind of sense. I assume this is 16. No, maybe not. 8? Yeah, it was 8. I keep forgetting. And if we pass in signed instead, negative 44, then X2 is going to, oops, it's going to be negative 42, right? Yeah, because this time it's signed. We won't play with the little and big Indian stuff. Ooh, unit 1. What does this mean? 8 unit 1. Unit integer. This is the size of each segment in bits. It is set to default by 1 for integer and floats and 8 for binary. What does that mean? Does that mean that it's going, I don't understand, the size of each segment in bits? Let's try this. So it's just 72. Maybe it doesn't change anything. But if I change this to 8, oh, I see. So this is 8 bits, but the unit here, does it end up multiplying it, basically? I don't think so. I don't think this is how it works. Oh, it does. I see. It's kind of like, how do you break this M up? How many of them are there? If it's 8 bits and this is 8 bits here, there's only one of them. If this is 8 bits, but there's like 1 bit each, there should be 8 of them. I guess, right? Let me see if then 2 and 4 should work also. Yeah. But if I change this, this won't work, right? Yeah, that doesn't work. You can see there are more than one way to read, store, and interpret binary data. This is a bit confusing, but still much simpler than using usual tools given by most languages. I still don't agree with this. I feel like other languages make it better. I feel like C is pretty low level and easy. I bet Zig and Rust are pretty easy too. Programmatically manipulate icons in HyperTalk. That sounds cool. The standard binary operations, shifting bits to the left, right, binary and or XOR and not, also exist in Erlang. Just use the functions BSL, BSR, BN, BOR, BXOR, BNOT. So if we have, so binary is 2 hash, right? 1, 2, 3, 4, and we're going to bit shift it to the left 1. Now this number becomes 2, right? And if we bit shift it by 2, then it becomes 4. Um, and obviously we can do uh, right? We're just saying that these are the same, so they pattern match with each other. I'm bit shifting it to the left twice, and that generally multiplies whatever number you have. So if I gave it a number like 48, bit shift to left 1, that should double the number, 96. And you should half the number when you bit shift right by 1, so it's 24. And we'll believe them on the be or, all that kind of stuff. With that kind of notation and the bit syntax in general, parsing and pattern matching binary data is a piece of cake. One could parse TCP segments with code like this: source port 16, destination port 16, ACK number 32, blah, 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 blah. And then the rest payload binary, some binary. Yeah, so if you had some binary, you could break it up into its segments. Attention! Erlang is slow compared to languages like C or C++. Unless you are a patient person, it would be a bad idea to do stuff like converting video or images with it, even though the binary syntax makes it extremely interesting, as I hinted above. Erlang is just not that great at heavy number crunching. Take note, however, that Erlang is still mighty fast for applications that do not require number crunching. Reacting to events, message passing, etc. It can deal with events in matters of milliseconds, and as such is a great candidate for soft real-time applications. Yeah, like Discord and all these companies that use Erlang and Beam and Elixir, they end up coding with NIFs, native interface format, I guess. I don't know what it stands for. That will call into something like Rust for the functions that have to be fast. So that works out pretty well. I think it's a great combo where you have an orchestration system at the top level and a lower level language that it can integrate into. There's a whole other aspect to binary notation: bit strings. Binary binary strings are bolted on top of the language the same way they are with lists. What are they saying here? Bolted on. But they're much more efficient in terms of space. This is because normal lists are linked lists, one node per letter, while bit strings are more like C arrays. Bit strings use the syntax, the angle brackets. This is a bit string. The downside of binary strings compared to lists is a loss in simplicity when it comes to pattern matching and manipulation. Consequently, people tend to use binary strings when storing text that won't be manipulated too much or when space efficiency is a real issue. All right, so this is something to note. I made a little cheat sheet here. I want to add, I think I'll easily get confused between these two. Here are my data types. And there's bit strings. These are actually using binary notation. Like this will be more efficient and faster. And what is the other one called? Normal list or linked list, but I don't, where was it? It was like up here where it showed us it was lists. Here. Erlang strings. Strings are lists that, so let's just go like strings, I guess. Strings are just lists where each element is a character. It will print the list as a string if all the elements are in the range of viewable characters. Otherwise, it prints it as a list. All right, so this is what it looks like, a list. Where is it? '65, '66, '67, ABC. And if I do ABC, yeah, it's going to print out ABC. So I'll just copy this. Okay, there we go. So now I'll remember strings are like lists and bit strings are these funky things. How long have we been streaming? Where is it telling me this? 1 hour. I must have like a little thing that's like, hey, it's been about an hour. Good job. We've been doing Erlang for an hour. Not bad. And look, we're like at the end of the section. We're just going to do binary comprehensions and then we'll be done. After this, I have to work. I also want to write a book. I have this crazy idea to write a book, so I want to learn how to use some of these, like, sort of writing systems with Markdown or whatever. I might do that on stream afterwards. All right, what is it saying here? Note, even though bit strings are pretty light, you should avoid using them to tag values. Yeah, like I'm assuming like these things aren't equal to each other, right? Like you can't do like hello. All right, so ABC is equal to 65, 66, 67, right? Yeah. And they are equivalent. All right. But I assume it's not equivalent to a bit string. Right, they're not the same. What if I use the loose equality? Nope. There must be some way to convert them from one to another. We will find out. Maybe there's like a way for us to see this here. Bit syntax. Data types. Bit syntax. No, this doesn't tell us. Binaries. This is what we were kind of like, they're binaries. Hmm. I wonder where like the functions would be. I'm sure we'll run into this. We can also ask ChatGPT later. All right, even though strings are pretty light, you should avoid using them to tag values. It could be tempting to use string literals to say something like temperature 50. I see, like basically using it as a key in a tuple, right? Um, Eric says, I need to get my static website blog generator toolchain set up. Tired of editing raw HTML. Exactly. Except I want to make some docs. I think I'll start. Okay, I'm going to talk about this later. I'm going to pause. I'll talk about that later. Temperature 50. Um, we don't want to use temperature as a string here. I think when we use like TypeScript, a lot of things, everything's just strings. But it's better to avoid them. It's just not as fast. So use atoms when you do that. Just make something called temperature, just like this. Temperature 75 if we're doing Fahrenheit. And there we go, rather than either temperature or temperature. Oops, I put an R in the end. There you go. Those are both no-nodes is what it's saying. Previously in this chapter, atoms were said to be taking only 4 or 8 bytes in space, no matter how long they are. By using them, you'll have basically no overhead when copying data from function to function or sending it to another Erlang node on another server. Conversely, do not use atoms to replace strings because they are lighter. Strings can be manipulated, splitting, regular expressions, etc., while atoms can be compared and nothing else. Yeah, although sometimes we take atoms and then we turn them into strings, it's just not a generally good idea. All right, guys, we have just a little bit more. I am amazed at how long it takes me to get through stuff. I think it's because I just talk a lot. Right? I mean, if I just did it, it would be so much faster, right? Also, I think I like to play with it to make sure I really know it. Okay. Binary comprehensions are to bit syntax. I guess that's called bit syntax, is what list comprehensions are to lists. A way to make code short and concise. They are relatively new in the Erlang world as they were there in previous revisions of Erlang, but required a module implementing them to use a special compile flag. Now, since R13b, they've become standard and can be used anywhere. Thank you, Eric. So here we go. It looks a lot like list comprehensions. Let us type this in here. We have X. Um, and we put the X inside of the angle brackets. And instead of the less than hyphen, we do less than or equal to. I guess that's special for the binary comprehensions. And now we're going to pass it some binary stuff. Let's not put in any conditions here. And we end up getting exactly back the same thing we put in. So these are bytes, right? So I can do this, right? Yeah, I can add the :8 to everything and not change anything. Um, just making sure I understand. And obviously, we should be able to do this too, putting the 8 on the initial X that we're assigning it to. And then we print out X without the And if I put x inside of a binary string, then it's alone. Okay. Think I understand. And then now we add a condition where we say x, we only want in here, we keep using the even example. So we say x has to be even. And now we only have 2 and 4 inside of this list. So we're basically breaking out items from the binary string and putting it into a regular list in this example. It does make me wonder, like, can I put things into 16 bits here? I'm guessing not. Oh yeah, look at that. So now it's going to combine these numbers into 16 bits. So 1, 2, you would, oh, right, because I put the REM in here. Let me get rid of this remainder. Oh, interesting. X is 16. So don't you expect to have 3 numbers? Maybe the last one doesn't fit. Let me add an extra one. Yeah, and that added a last number. So that's cool. It can, if it can't fill it in, it's going to drop it. So 1 and 2 basically get put into a 16-bit number. I guess the 1 is going to be the first on the left side, right? Which makes it like whatever, a large number, 256. And then adds 2 to it, which is why we end up with 258. So if the first number is 0, we're just going to end up with 2, right? Watch. Whoops. As the first number here, because it's 2, the 0 here means nothing, and then we just read the 2, which is normal. So this makes perfect sense. That's really cool that we can understand this. Hey, person from Brazil. How do I say your name? Poisnada? Poisnada? Pois in French is like peas, and nada must mean nothing, right? I think I know that much. Pois also, no, never mind. All right, the only change in syntax from regular list comprehensions is the less than hyphen, which became less than equal, and using binaries, the angle brackets, instead of list, the square brackets. Earlier in this chapter, we've seen an example where there was a binary value of many pixels on which we used pattern matching to grab the RGB values of each pixel. It was alright, but on larger structures, it would become impossibly hard to read and maintain. The same exercise can be done with a one-line binary comprehension, which is much cleaner. So we have these pixels. I think I still have my pixels variable in here. No? How's that? So I'll just copy this. All right, what are they trying to do? They're trying to get RGB. They're trying to break it up into a tuple that they can manipulate, right? So now that we know that, let's go ahead and try to do that without looking at the thing. So let's just, like I do before, let's just try to print out the same thing that we get. So here's a list comprehension. The problem is, like, I think I've used a lot of these variables. Let's see, does P exist? No, it doesn't exist. So I can do P for pixel, P, and this is 16 bits from the pixel thing, right? And we do less than equal to assign it, and then we're giving in pixels. I think that is the way to do it, right? So now we have, that's not right. We want to do R. I think we want to do R. No, they were 8 bits. Didn't I say they were 8 bits? Yeah. What am I talking about? I keep forgetting this. RGB. Which means this one thing is 24 bits, right? So I can do P24. There we go. Yikes, why didn't that work? I think it may work. And now I want to break up this thing, each of these pixels, into 3 values. So we do RGB, R, G, B, right? And here we turn this into a tuple, R, comma, G, comma, B. And now we have a list of pixels. We have 4 pixels. Let's see if we did this right. Yeah, except, oh, here's their answer. Yeah, that's how they did it. Yeah, it's the same thing. And we got the same answer. Another binary comprehension syntax exists to let you do the exact opposite. What do you mean opposite? Um, oh, I see. Constructing. This I want to see. How do you construct? I see. We're constructing. Sorry, I'm just trying to understand this. So, because the outside is not a list, it is a bit notation. So that means the outside we put in the angle brackets, and we're still doing the notation for comprehensions inside. We're taking the RGB, which that's the the tuple. So here, let me do the same thing. RGB is equal to this. So now we have this. What do you want to build with it? How's the checking going? What checking? Um, so for the Erlang, I just program a lot of Elixir, and Elixir calls into Erlang, and when you run the static type analysis with dialyzer, the errors sort of like print out in Erlang format. So I just think like it's very useful to know Erlang, but also, we'll see what happens. A lot of people ask me like, "Hey, why are you learning this? What are you going to do with it?" And like the answer is like, yeah, I build distributed systems in general. Uh, I don't build like websites. I build much more on the server side of things. Um, but yeah, I just also just enjoy learning this stuff. So if I never use it, that's fine. How about you? What do you do? Okay, so we have a list of tuples now, and we want to convert it back into the bit string or whatever it was called. Let's figure this out. So we have to have something like R, G, B in here, but I don't think I can actually, can I use the same variables? We say here, and we need the RGB that we pulled it out into. There's a tuple in here. that we're reading from RGB, because RGB is a list, right? Since it's a list, we use the less than hyphen arrow, and this list is going to break it up pattern match into the individual tuple. We deconstruct the tuple into RGB, then we break it into this bit string here, or whatever they call it, RGB. It defaults to 8 bits, so I don't think I need to say anything more here. And I think that's it. And this should be the same as pixels, right? I should be able to do equals pixels. Oh, shit. It looks slightly different. Here's pixels. Oh, some of the things. Did I? RBG. RGB. I must have screwed up like the B and the G somewhere. Oh, it's because it should be this. RGB. RBG. This is dyslexia. There we go. Now it's the same. Oh, cool. Full stack web. I'm doing some TypeScript for work, so I've had to learn it. I actually had a couple of streams where I learned TypeScript so I could get the job and actually program with it. Oh la la. All right, so we learned how to construct a bit whatever syntax thing from tuples using comprehensions. Be careful, as the elements of the resulting binary require a clearly defined size if the generator returned binaries. So what is this trying to say? This is a list with a single binary. It goes into bin, which is a binary now. And what the, no, this isn't right. Yeah. How complicated. It is also possible to have a binary comprehension with a binary generator given the fixed sized rule above is respected. Yeah, so this is just going to pull out each individual element, add one to it, and print it out. All right, well, let us consider this done. So I think we're going to stop on Erlang for now. We'll continue with it later. We did all the data type section here. Where's the table of contents? Here it is. So we did all of this starting out for real. Then we're going to do modules. So modules, syntax, types, recursion, higher order functions. That sounds fun. Errors and exceptions, functionally solving problems, short visit to common data structures, Hitchhiker's Guide to Concurrency. This will be fun. Multiprocessing, errors in processes, designing a concurrent application. What is OTP? Wow, this has a lot. Clients and servers. Rage against a finite state machine. I wonder why it says rage. Event handling. Who supervises the supervisors? Building an application with OTP. Holy cow. Building OTP application. The count of application. Release is the word. Leveling up the process quest. Buckets of sockets. United Nations Council. Bears ETS beats. This is like a Redis sort of thing. Distribunomicon. Distributed OPT applications. Common test for uncommon tests. Amnesia and the Art of Remembering, Type Specifications and Erlang. This must be Dialyzer. Conclusion. All right, that's a lot. Holy cow. Exploitation. All right. Thanks for hanging out. I think I'm going to stay streaming, but I'm going to switch gears. Just have to figure out whether it's going to be for